Okay, so for today's exercise, we're going to change over to a new test that we haven't tried previously. We're going to measure heat tolerance in an ectothermic animal. We're going to go ahead and use goldfish because they're easily obtainable, they're relatively hardy, and they usually respond really well to temperature trials. So the idea is to determine the highest and or lowest temperatures at which an animal, an ectotherm in this case, can survive. And so what we're going to do today is just begin by looking at goldfish that have been kept at room temperature for several days. So they've acclimated to those particular temperature regimens that they've been exposed to, partly in the pet store and partly up in the lab. And what we're going to do then is calculate the critical thermal maximum number for the population of fish based on the individual responses. So if we want to talk about what a critical thermal high or low temperature might be, I put up this graph that I'm hoping might be helpful. So usually when we write these things and we have acronyms that we use to talk about various types of procedures, we just use abbreviations. We use CTM, that stands for Critical Thermal Methodology. Now, the critical thermal methodology can be used then to determine critical thermal maximum temperatures, the highest temperature that they can live at for a short period of time, or critical thermal minimum temperatures, that's the temperature, low temperature that they can survive for a short period of time. So just to give you an idea of how this works, if we have fish at a given temperature, an acclimation temperature, and we talked about the acclimation temperature that we see in the fish that we have in the lab today, is about 24 degrees C. Okay, so 24 degrees centigrade is the temperature that we start these fish at. They're acclimated to that temperature. As long as they stay at that acclimation temperature, it's within their acclimation range, and so they do just fine. To test how high we can go, and we'll use the high number, but we could turn this graph upside down and measure the low number as well. We'll just look at critical thermal maximum to get the idea behind this. The acclimation temperature then is here on the temperature axis, and at some point then we begin to increase the temperature. Now, the other thing that's happening is we've got two things going on here. Ordinarily, in a good experiment, you just have one factor that's being changed, and all the rest remain constant. In critical thermal maximum temperatures or minimum temperature determinations, we have two factors that are going on. Time is moving and the temperature is moving. But we get around that because time over temperature equals rate, and so, I guess it's the other way around, but if we have rate of increase, the rate of increase must remain constant. That's the deal there. So we do still have, we haven't really violated that rule. We still have an independent and dependent variable on the graph. And the vector there that you see is simply the rate of temperature change. So as that begins to increase, the fish, of course, are exposed now to higher and higher temperatures, and usually we try to keep this rate relatively low. So, for example, somewhere between about 0.3 and 0.5 degrees change per minute is usually the rate that we like to get. That's a rate that's fast enough that it doesn't allow the fish to acclimate during the trial to the higher temperatures, but slow enough that the fish's body temperature keeps up with that rate. That's the key characteristic then for determining your critical thermal maximum or minimum temperature. So as we increase the temperature, the fish gets a little warmer and a little warmer and a little warmer, and before too long, it becomes uncomfortable, and you'll usually see some behavioral changes. We'll see the fish will become much more active. There might even be some escape maneuvers trying to get away from the warmer temperatures in the case that we have here anyway. Now, when that happens, we usually have a couple of different endpoints we can look at. We can look at muscle spasms. This occurs when temperatures get high enough that muscles begin to release calcium and they go into uncontrollable spasms. Certain animals show spasms really, really easily, others not so well. It's been my experience that most fish don't show spasms until it's too late and they won't recover. And that's one of the key things about a critical thermal maximum or minimum test is that the fish should recover. In fact, if we have fish that die during the trial, we don't use them in the analyses because we've obviously exceeded their critical thermal maximum. The critical thermal maximum should be survivable. In other words, it's the highest temperature that they can hit and still, when returned to their acclimation temperature, recover. Okay, so that's the key. This point you see here, we call LOE, loss of equilibrium, or muscle spasms. I prefer loss of equilibrium because it's a much easier endpoint to observe, and again, some fish don't show muscle spasms, and so that's a problem. But they all show loss of equilibrium. In other words, the muscles become unable to maintain coordinated activity, and so the fish flips upside down. And we refer to that as the ecological death temperature. What that means is that endpoint in nature would be lethal. Either the fish, A, has lost the mobility to escape from conditions that would kill it, the temperature conditions, or in a lot of cases, once you're a fish and you flip upside down and are thrashing around, something's going to come by and eat you. So we refer to that as being exposed to the ecological death temperature. If, however, we return that temperature back to the acclimation temperature when they experience LOE, the fish will recover, and we can use that data point then to calculate the critical thermal maximum. Now, if we continue to increase the temperature, we reach what we call physiological death. Nobody comes back from physiological death. There is no recovery from that. So we try to avoid that when we can. So again, if we reach our LOE temperature and we record that, we return them back to their previous acclimation temperature, the fish should survive. So with that in mind then, this is a technique that's been around since the 1920s or so. It was formalized by a couple of people working with reptiles, desert reptiles, in 1944. And since then, there's been several makeovers, but the test itself has remained relatively unchanged. We have done literally thousands of tests on ectothermic animals using this procedure. So it's widely used. It's especially useful now that things are starting to warm up and we need to know more about what fish or certain invertebrates, how they're going to respond to these changes in temperature. And we can use this method then to determine it. But the other nice thing about this method is you don't need anything really special. We need a heater and we need a tank to put the fish in, and we need the ability then to maintain a constant rate of temperature increase. And so usually we write a table like this. This would be our table that we would put into our lab book, and whatever the temperature was, right, times 0, what was the temperature, and usually at 5 to 10 minute intervals we would measure another temperature and put it on the board until we reached loss of equilibrium. Okay, so we've got some idea of the theory behind the test that we're doing. We're going to measure temperature tolerance of these animals, in this case upper temperature tolerance, and then we're going to go ahead and graph that so that you can see how that works as well. We've got the setup here. A couple of things that you need. We need a water bath, which we've got here in this clear plastic tub. And then we have the fish themselves, and here are our goldfish. We're going to run 3 at a time so that we get replicates of 3 every time we run a trial with this. These fish have all been acclimated, as I know, to room temperature. So that's where we start, and we will increase the temperature slowly until they lose equilibrium. The second thing that we have here is this is a 300-watt titanium heater. The heater heats extremely fast because you can see there's a relatively small amount of water here. So 300 watts is going to cause that to move, the temperature to move really, really quickly. And so we want to avoid that. So we instead run this through, we can see we've plugged it in already. This is made by a company called Glasscall, but it's an intermittent timer switch. And so when the light is on, the power becomes active here at the switch, and therefore the heater will heat up a little bit. And then when the power is off, the heater cools down a little. And so by adjusting the percentage of time, it runs from 10% to 100% on, we can control the amount of heat that goes into the system. Okay, so we're going to go ahead and put the heater, the titanium heater, into the water bath. A couple of things about titanium heaters, and I know you guys aren't here to do this, but you never take them out of the water while they're on, or even shortly after you've unplugged them, because they will burn themselves up. Okay, and these heaters have no control on them. In other words, they will continue to heat up until the water is boiling in there like soup. And so that's why we plug it into the Glasscall so that we can bleed the heat in a little bit at a time. Okay, so that's what we're going to do. Okay, so here are our fish. We have 3 fish. We just number them 1 through 3, and we will put them into the water bath. We'd like to have some little space in between them. And we're going to let them sit there for just a minute or two to get used to their surroundings. We're going to go ahead and take a pump to circulate the water inside the water bath, so that, this is just a tiny little mini pump that pushes water around so that we get even distribution of the temperature. Okay, so go ahead and put that. I usually like to put it so that it blows across the heater itself. Make that happen. Okay. All right, so I'm going to go ahead and plug that in now. Okay, so we've got water moving across the heater and circulating inside the tank. Again, give a little space in between each one of the beakers so that the water circulation is complete. And we don't have, it's not unusual to have one of the glasses, maybe, or one of the holding tanks to be a little bit warmer than the other. Keep in mind that as long as we stay within that range of temperature increase, that's not going to matter. It's CT max will be the same. So if it's 0.4 in one, but it's 0.5 in the other, those two things, one will finish first, but they'll still reach the same temperature, or close to the same temperature. Okay, so what we're going to do is I'm going to plug in the glass call, and now we're going to start a timer. So let me go ahead and I'll plug that in, and we'll start the timer. It's going. So you see the lights on, so we're starting to send a little bit of heat in. What we're going to do then is we're going to take measures at every 5 minutes, so we'll get the initial temperature in the tank, or in one of the glasses. We don't generally measure the tank. The tank temperature will be slightly different than the beaker temperature that the fish is in. Right now they are at 20.6 degrees is our initial temperature. I'm just going to go ahead and leave that in there so we don't have to look for it every time. Okay, 20.5 was our initial temperature. We'll put that on at times 0. Okay, and so now we simply go through the routine of every 5 minutes, taking the temperature, writing it down. What we'll get is, in the end, we'll be able to go ahead and plot time or temperature on time, and that'll give us our flow rate, right? The slope of that line will give us the temperature change rate. And so that's how we know we've got a good number then, because we can see it will come out when we plot it as a straight line. Okay, and if we just take a look at the fish in there, see that they're relatively calm and collected. They don't seem to be in any distress. It's always good to go ahead and include a description of the progression of behavioral changes that you see in the fish or the crab or whatever animal you're working with. Remember, this only works on ectotherms. It doesn't work on homeotherms. So this is a really good test. Again, thousands and thousands and thousands of fish species and also crab species. Just about any ectotherm you can think of, somebody's done a critical thermal maximum study on it. Okay. All right, we're going to go ahead and let this run for a little while, and once we start to collect a little bit of data, we'll come back then. Okay, so what we're looking at now is the end of this trial, this first trial. You can see that the 3 fish that are in the beakers have become much more agitated. The the temperature of the water has gone up. We started with a temperature of 20.5 degrees centigrade, and now we are at 34.3, and so they're approaching that point at which the critical thermal maximum will be reached, and at that point they'll lose locomotor control. Again, that's a ecological death point, and we will take them out, put them back in their original tank at the temperatures, the original temperature, about 20 and a half degrees or so, and that'll allow them to come back and recover fully from the experience. The number then that we get, the average number that we get for these three specimens then becomes the critical thermal maximum temperature for this species. So that's what we're going to use then to compare to other species in the literature. So your job then will be to go ahead and calculate the overall rate of temperature change, and then to look at the get an average number for the critical thermal maximum temperature for goldfish. We'll have a second run that we will provide data for then for goldfishes that have been acclimated overnight to a higher temperature, and we should see some changes in those. Okay, so now you can see that the goldfish are much more agitated. You can see the respiratory rate's gone up precipitously. The both fish are showing initial stages of loss of equilibrium, trying to swim down to the bottom, and their air bladder, which is or swim bladder, which is not at the center of gravity, tends to work against them as they lose muscular control. So in a relatively short period of time here, we should be able to see loss of equilibrium. Okay, so you can see that the fish in the first beaker now is coming up on loss of equilibrium. He's lost side-to-side orientation, and movements have become much more urgent. Oftentimes you'll see high levels of activity, and then they'll slow way down, maybe roll over with initial loss of equilibrium. Shortly after that stage, they should show complete loss of equilibrium, and may also show muscle spasms. So at this point in the procedure, you can see that the fish now is relegated to just short bursts of movement and has lost the ability to escape the conditions that ultimately will result in its death. And so this, we're going to go ahead and take this temperature right here as the muscle spasm temperature.
36.8.
So 36.8, and we're going to go ahead and pull them out and restore them back to the acclimation temperature. Okay, and the last fish is getting into that same stage where it's ineffectual movement. Even the opercular movements are limited. So we're going to go ahead and call that temperature this CT max for this particular
36.9.
Okay, so you've seen the procedure. We've talked about the theory behind that, and what we're going to do is we're going to take the goldfish that are unused, and we're going to increase their temperature overnight to 30 degrees, and then we'll rerun the same study on a different group of fish that have now been acclimated at a higher temperature, and we should get some inkling of how fast fish can respond to changes in water temperature. And so that'll be the next step that we will do, and we'll pick up there and after we've got the setup ready. Okay, so we have had fish, goldfish, acclimating at 30 degrees overnight, and what we're going to do then is redo the study that we did yesterday,
this case with goldfish that have partially acclimated to a new temperature. And so what we would expect to see is that the temperatures that we get from this group of goldfish will be significantly higher than the ones we got yesterday for fish that were acclimated at 20 plus or minus degrees. So you can see in the tank, show you the fish all set up, and they have been sitting there all night. We've got, again, the heater in there, the 300-volt heater. It's on the glass ball controller, which would allow them to turn on and off the power so that we just leave the heat in a little bit at a time and under controlled conditions. We have a pump, a little tiny circulating pump to move the water around. Not for the fish's sake, but just to make sure that the temperatures are uniform. So very similar to last time, we're going to start by going up to the board, and we're going to put our first temperature in, and then we're going to continue collecting temperatures over the next probably 30 minutes or so. And then once the fish look like they're starting to approach their critical thermal maximum limit, we'll go ahead and have you guys join back in. So we're going to turn it off for right now, and we will come back to this when we get closer to the end.
All right, so we're switching over to me for a second. We're at the point of LOE for one of our fish. So we're going to go ahead and take the temp in that water there to get the measurement. And Dr. Bennett will be back in a little bit to give you guys a conclusion on that. But we should be seeing now that as they've adapted to a higher temperature, their LOE should have increased. So their critical maximum should have gone up with adapting to a higher temperature. And this guy is looking like he's at 36.2, which is about the same as yesterday, but we will keep an eye on the other two still look like they're still shrugging, so we will see how that ends up. Alrighty, it's been about another 10 minutes, and it's looking like fish 2 is getting close to that point of LOE. And so Orculums and the floating place that recovered those gills aren't really moving much at all, so his respiratory rate is going really down. He's kind of spazzing out quite a bit. He's starting to lose equilibrium, starting to tilt side to side. So I'm going to give him another maybe minute here, see if he corrects himself. But if not, I'll call him, take his temp, and then we'll just have one fish left to go. And that's a full sideways, so I'm going to go ahead and call him. You're at about 36.9, I'm going to say. And while I'm thinking of it, I'm going to show you what we do once we are done with them. Here. So what I'm going to do, I'm just going to put him right back into the acclimation tank he was in. That's the one on the left. You're going to kind of see him do a little bit of a twirl because he's really unbalanced right now. But rest assured, he's going to be fine. If the camera will cooperate here. There we go. That'll do. So he's going to probably twirl himself down the bottom, but he will be all right again. In time. There goes the alarm. You can see the tank on the right there. Those are our fish from yesterday. They are perfectly fine. They do recover from this experiment. But I'm going to keep it going, and I'll bring you guys back when the last fish is ready to go. Alright, we are now hitting some major muscle spasms, and he's starting to lose his equilibrium, so we're going to call this guy too. And he came in at a whopping 39.1. So this little guy made it quite a long time. So we're going to log that final temp for you guys, and we're going to wait here for Dr. Bennett to come back for him to make some potential conclusions from the temperature changes. So we will be back with Dr. Bennett shortly.
Okay, so we've had the opportunity now to run two different treatment groups of goldfish. One at a lower temperature, one at a higher temperature, but occurring within 24 hours of the first measure. Now these were independent samples, so it's not the same fish that went into each trial. So your job then is to, of course, calculate the rates of temperature change, and then also to look at the mean values for both of experiments, one that was done at cooler temperatures, and then those fishes that were acclimated at warmer temperature overnight. And run a t-test on that and see if there's a significant difference between those numbers. So hopefully you've learned a little bit about how fish respond to changes in their temperature environment. They do have the ability to modify their physiological processes in ways that optimize their performance at different temperatures. And you, I think, can see from the data, even the raw data, that those changes can happen relatively quickly. And so for fishes that live in relatively austere environments, goldfish would count as that. They are a member of the carp family, but they tend to live in shallow waters where big changes in temperature happen all the time. And so by being able to manipulate their thermal tolerance, they can live in much broader range, geographic ranges, and across much greater ranges of temperature as well. So until next week then, that should take care of us for today.